Hello everyone, Mr. Lee here. In this video, I'm going to go over the universal law of gravitation. Okay, so with this law, I want to take you on a little mental journey, a little mental experiment. All right, so let's say you're outside, it's a summer break, and you have like a 5-year-old little niece or nephew, right? All right, so you're out there, and up in the sky, they see this moon. They see a moon. They see a moon up in the sky, and they're asking you, hey, why do we have a moon? Why does the moon move across the sky? You know, why does the sun rise? And they just kind of snowball like 5-year-olds do, one question after another, and you're trying to come up with the best answers, but you're only getting a reply of why. You could be like, well, the moon is orbiting the Earth. Why? And then you're stumped, right? And like they go into the sun, like why does the sun rise? Why does the sun set? And then you try to explain everything and say like the Earth orbits around the sun, and then you're like, why? What's orbit, right? And then you're like, I don't know what to do. Now, I can't help you for that exact situation because we're going to be using some pretty technical stuff. But for you, my wonderful students, we're going to be able to answer some of those questions. All right, to start off, let's go over the equation for the universal law of gravitation. So with this equation, there's a couple of things. This is a subscript of capital G. Okay, not to be confused with the subscript of lowercase g, which we use for the weight equation or the force of gravity. Okay, so how we call this? We call this the gravitational force, not to be confused with the force of gravity. Okay, so this is the gravitational force. So if you're still in the habit of, if I were to ask you a question like, why do things fall to Earth? You're like, gravity! Or like, what is this G stand for? You're like, gravity, right? If you're used to just saying gravity for everything, we gotta stop. Because now we have the acceleration of this gravity, the force of gravity, and now we have this gravitational force. And I'm about to throw you one more thing at you. We have this constant. Okay, so this is something that applies to every single thing in the universe. It's a capital G. And we're gonna go into the history of how we found this constant. But this constant is called the gravitational constant. Okay, so now we have one more thing that we're going to add to the gravity little vocabulary terms. Okay, so we have this G, and we multiply that. Now you'll see this in different ways. I'm going to show you just the way that I will use it. M1 and M2. Okay, so these M1s and M2s, these are multiplied. So what this shows is that we have two masses divided by this r squared. All right, so let's go over here. The m's, they stand for masses, okay, or a mass. So we have two different kinds, and here we have what we call the distance. Okay, now sometimes you might see this as radius. Okay, and you're like, wait a minute, radius? I know that term. Like that's a distance from the center of a circle to the outermost edge of the circle, right, to the circumference. Well, yeah, technically you're right. So from here to here, like that will be a radius, and that is the same kind of radius that we're going to be talking about. But oftentimes you'll see it just written as the distance. Okay, and we'll go over why that is in just a little bit. All right, so this is our equation, and we're going to go into the history of the gravitational force. It's really cool. So once upon a time, there was this guy. Dr. Cavendish. I don't know if he was a doctor, so we can call him Mr. Cavendish if he wasn't a doctor, but he was a really smart man, and he wanted to test out Newton's laws. And so he had this really, really cool contraption. And this is something that you could actually set up yourself if you have the time and like if you have a digital camera and the memory space to film this in action. But what he did, I believe the story goes, he had a room in his house with nothing else in it, and he had like a closet. And so he did this experiment in the closet, like just to be sure like no variables affected this. But what he did is he got a mobile of some sort. So a mobile is kind of like that thing you put above a crib, and like the babies look at it as like spinning around. They're like, ooh, right? And they're like fascinated for hours. And so he had a mobile of some sort. And he also had, so each of these mobiles had like a different mass, right? So, or it had a mass, not a different mass. So this was M and M. And this mobile was able to spin freely without any friction, or as close to frictionless as possible, right? And I'm just gonna put that on like a ring stand. I don't know if he used a ring stand, but for the sake of my story, let's say he used a ring stand. Okay, so in case you do want to do this. And then what he did was he got, so if this is like the floor, right, we're looking at like the floor of his closet, he got a very massive object. Okay, so I will represent that massive object with a bigger ink brush, right? He got a very massive object, okay, and then we'll call this M, right? It's a pretty big object, and he put that massive object like on a stand, and he put it close. He put it close to this mobile mass. Okay, and so I'm having a hard time drawing in 3D, but I'll try my best. And so this mass, okay, these two masses, they were close to each other, and he had another mass, like let's say in the background here, right? I'm trying my best to draw 3D here, not an artist. All right, so he had a mass like somewhere in the back, so you got to imagine that this is 3D. So these two masses were close to each other, and these two masses, this is a horrible arrow, let me redraw that arrow, and these two masses were close to each other. Okay, and because this is where the genius comes in play, because right here it was frictionless and right here was frictionless, they were like, he tried to minimize as much outside forces. I'm not saying he used WD-40, but I know in this day and age we will probably use WD-40 to reduce that friction. Okay, and so what he did was he looked through like a glass or like a lens, and he was able to measure the distance between these two objects. He was able to measure that distance between two objects, and what he found was that over a long period of time, okay, these two objects would start to be attracted to each other, and these two objects were attracted to each other. And so what he saw was like this mobile would start to rotate. A really cool phenomenon. Like it was amazing. And so what that showed was, and these were not magnets, by the way. These were not magnetic material. So he made sure of that. Like he tried to reduce as many outside forces, and like it blew his mind. It blew the scientific community's mind, because we finally got evidence for what Isaac Newton was saying all along. Okay, and so with this, he was able to do some calculations, and with this equation, okay, f of g is equal to g, the gravitational constant, times m1 times m2 divided by r squared. He was able to come up through the calculation this gravitational constant. Okay, and I'm about to show you what that value is down here. He found that the gravitational constant, and this is something that is on your equation sheet, but you should definitely have this around, was I think it was like 6.67, but we're just going to round up to 6.7 times 10. Oh my gosh, 10 to the negative 11, and the units are Newton meters squared divided by kilogram squared. This gravitational constant, so I'm going to write that again, 6.67 times 10 to the negative 11. Okay, this right here. Now, what's so cool about this? Okay, so what Cavendish did is he showed us that with his experiment that any two objects in this universe are attracted to each other. Okay, so if we were to think about this, we know that we have here the Earth, right? So I'm going to draw the Earth for us, and I guess earthly blue, right? Yay, we have the Earth, and because we have like trees or what's left of the rainforest, right? We have the Earth, and then we have a moon over here. So this is like a celestial form of Cavendish's experiment. So instead of having a mobile, like with two objects hanging, we just have one object hanging, and we have another massive object here. And so what he found out was one of the reasons why this moon is attracted to the Earth is because what Isaac Newton said, like all objects are attracted to each other. And so what we find here is that the distance from the Earth to the moon, that's our r, or our radius. And the reason why it's radius is because we're looking at a circular motion. Okay, so it doesn't matter if the moon's here or if the moon's here or if the moon's here or if the moon's here, right? The radius, well, there is some slight changes because the moon doesn't orbit the Earth in a perfect circle, right? But like basically it's a circle. So it doesn't matter where the moon is away from the Earth, it is a distance away from the Earth. And because the Earth and the moon both have masses, so I'm going to go back to the equation, f of g is equal to capital G times m1. So in this case, I'm just going to write it as me for Earth and mm, so mass of the moon divided by whatever the distance is between the Earth and the moon. Okay, we find that the two celestial objects have a force. So what this shows us is that Earth is pulling on the moon. Really super cool. Because now, like, you're able to answer why the moon orbits the Earth, right? Like, it's being attracted, it's being pulled towards it. And in this unit, we're going to go into exactly why. Like, I use the words carefully, right? I said the Earth pulls the moon. So, and so normally when you pull something like towards you, it comes towards you, but like the moon hasn't crashed towards the Earth. So, we'll cover that in a later video. So we know that there is a gravitational force from the Earth that pulls on the moon, and according to Newton's third law of motion, we also know that the moon also pulls on the Earth with the same amount of force, and that is the key here. If we take a look at this equation, I said same amount of force. So we can rewrite this equation as, instead of the Earth pulling on the moon, we can say that it's the moon pulling on the Earth. And it doesn't matter, because according to the laws of math, it doesn't matter which variable comes first when you're multiplying, right? You're just multiplying together. And so here we have the formula to see exactly with how much force the Earth pulls on the moon. And this also applies to something like the sun, right? So if we have the sun, so we have the sun. Whoa, I'm the sun. I'm the sun. I provide life for everything, but it's just on Earth right now. All right, so we have the sun, and let me draw the Earth. All right, so here we have Mercury, Venus, and Earth. All right, so we have the Earth right there. Okay, and the reason why I drew the Earth as such a tiny little dot is because, you know, compared to the sun, the Earth is tiny. And so the distance, I'm going to go from the middle, okay, the distance of the radius. So the distance from there to there is r, and we know that the Earth orbits around the sun, so it doesn't matter. This is pretty close. I'm pretty sure I drew the sun way too big. If you're any astro people out there, but with that distance, we can use this equation: f of g is equal to g times m sub s, being the sun, and m of e divided by whatever that distance is squared. We can see exactly how hard this Earth is pulling on the sun. Now, it's hard to imagine this, but if according to Newton's laws, yes, the sun pulls on the Earth, and we know that because, you know, we are in orbit, and we are within the sun's gravitational field. But according to Newton's laws, the Earth is also pulling on the sun. That is super, super nifty. Okay, now if you're thinking, like, take a look, right? Look around you, and like, you should see objects. So you might be thinking to yourself, wait a minute, Mr. Lee, wait a minute. Are you saying that according to this equation, right? So let's say this is m sub l Lee, and this is, like, I don't know, what do I have close to me? I have a fan, right? This is the mass of the fan. So what you're saying is that I am attracting the fan, and the fan is attracting me? So if I were to draw it, it would look something like this. So this is, hello, my name is Mr. Lee. I'm here to teach physics, and I have a little fan, right? I have a little fan right there. Okay, and the answer is yes, because I have mass, and because the fan has mass, we both attract each other. Whoa! Now this is really nifty, because this goes against what we know about what happens in our day-to-day lives, right? Like, if you're walking down the street, you just don't see, like, leaves being attracted towards you, or like cars, like, you know, flying through the air because you're attracting them, or like, you know, blades of grass like just tilting towards your direction. That doesn't happen. And to see why, let's take a look back at this G. Okay, let's take a look at this G. This is 6.67 times 10 to the negative 11. So what that comes out to be is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11? No, excuse me. 10 zeros, and then we have 6 point. So 6. There we go. All right, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, there we go. So this gravitational constant is a very, 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 very small number. Okay, very, 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 very small number compared to, you know, like our mass. So my mass, right? I have a mass of 75 kilograms. So 75 compared to 0.0000000000667 is really, really big. And so this gravitational constant, if we take a look at this equation, right, when we multiply something very, 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 very small, compared to other things that are big, it's very non-noticeable, right? And so even though I'm attracted to the fan and the fan is attracted to me, like it's hard to notice. And plus there's like frictional forces that are involved. But more importantly, if we take a look around, right? I take a look at the fan and then I zoom out, right? What do I see? My house. I zoom out again. What do I see? Maryland. I zoom out. What do I see? North America. I zoom out. What do I see? I see the Earth, right? In terms of the grand scheme of things, there is a even bigger mass that both myself and the fan are attached to. And because the Earth has such a big mass, right? Because the Earth has such a big mass, we're more attracted to the Earth than to random objects. And so we call that the force of gravity. Like we're attracted to the Earth. But according to this equation, even though we're attracted to the Earth, right? The Earth pulls on us. We also pull on the Earth. Whoa, right? Yeah, really, really cool things. And so this really shines light on Cavendish's experiment of how like phenomenal like doing that experiment is. And by the way, you can try this as well. You just need like an object hanging that's able to rotate freely, like I showed you. Another like massive object, like you could have bricks, you can have like weights. But if you set it up, you will see that the floating object on the mobile is attracted to the massive object. Okay, and so what this equation shows us is that the more massive something is, the more attractive it is. So if we were to compare the Earth and the Sun, right? The Earth and the Sun, because the Sun is so massive, we're attracted. The Earth is more attracted to the Sun than, let's say, to the Moon, right? Because the Moon is like compared to the Sun, the Moon's mass is nothing compared to the Sun's mass. And because the Sun has such a greater mass, it exerts a greater gravitational force on the Earth. Okay, but you might be thinking, well, if that's the case, Mr. Lee, why isn't the Moon attracted to the Sun? Well, technically it is. The Moon is attracted to the Sun, but because the Earth is so much closer to the Moon, right? And that's where this r squared comes in, because the Moon is so much closer to the Earth is able to exert a gravitational force on the Moon a little bit more. Okay, so this variable here, this will be the last thing that we go into, this r squared, that has a big impact on things. So the closer you are to other objects, the more attracted you are to the other objects, right? The more of a gravitational force you exert on other objects. So in this case, between me and the fan, if I were to step closer to the fan, I don't know why the fan got so big all of a sudden, right? The closer I get, the more the force is exerted. All right, now for the mathematical part of this, I do want to focus on this r squared. Okay, so I'm going to rewrite this equation, and I do suggest that you take a look into this as well. So I want this g out in the front, okay, because that's just a constant. And so what we have is we have the two masses, m1, m2, being multiplied. Okay, so we have g times m1 times m2 times 1 over r squared. Okay, so what I did is I just took this equation and kind of like split it apart. I split it apart so that here we have r squared as its own separate variable. This is what we call a inverse. I'll write this out because it's important. This is what we call a inverse square law. Okay, inverse square law. So what this means is, so inverse means that if one variable increases, as long as everything else remains constant, the other variable that you're looking at decreases. And so what I mean by this is, if we were to take a look at this equation, f of g is equal to g times m1 times m2 times 1 over r squared, and what we are changing is the distance between two objects. Okay, so we're not changing the two objects. So we have object 1 and we have object 2. So the two objects remain the same. But in an experiment, we bring the two objects closer and closer together, right? We bring the two objects closer together. So what we're changing is the distance between the two, the radii between the two, okay? So in this situation, the relationship that we're looking at is just between the force, the gravitational force, and the distance. Okay, because the gravitational constant is a constant, so it will never change, and the masses in this scenario, it did not change. So this inverse square law means that if we are increasing the radius, Okay, if the radius goes up, because it's inverse, the force of gravity will go down. So in layman's terms, if we separate the objects, right, we increase the radius, we separate the objects further and further apart, the gravitational force will decrease. And the opposite holds true as well. If we bring objects closer and closer together, excuse me, that should be downwards. If we bring the objects closer together, so we decrease the radius, that means the gravitational force will increase. Okay, so that's the inverse portion. Now the square portion tells us is that it'll increase at a square rate. And so if we were to graph something like this, right, f of g times the radius, okay, we will get something like this. So the smaller the radius, the closer it is, the greater the force. Okay, the further apart something is, the smaller the force. Okay, so we can see something like this. And because it's a square, we get a curve like this. Right, we get this curve. And so in order for us to linearize, if we were to have this data set, we would need to make the variable r look like this, 1 over r squared. And so if we were to regraph it to look like this, 1 over r squared, we will get a linear curve. Okay, and the slope for this graph will give us g times m1 times m2. Okay, the slope would equal to the gravitational constant times the two masses. All right. Okay, so hopefully you learned a thing or two about how objects are attracted to each other in the universe. Okay, just so you know that every single thing on this earth, you have a gravitational force exerting on it, and every little thing on this earth also pulls on you. If you're wondering, well, why aren't things flying towards me? Just so you know that you are on Earth and there are pretty massive things around you, namely the Earth. But just one last thing to think about: if you're an astronaut, right? So that's your astronaut helmet, right? And you're floating around. You're floating out in space, okay? And if you have a apple, why an apple? Because I don't know, Newton is associated with apples, I guess, right? So we have an apple. Okay, if it's just you and this apple just floating around, okay, and the apple is out of reach, out of grasp, okay, because you really want to eat it, because you're just floating out there in space over a period of time, because you two exert a gravitational force on each other, eventually you and the apple will meet. So that's a little solace if you're floating out there in space and you're hungry. All right, I'll see you next time. We will talk about the centripetal acceleration. Bye-bye.